All right, so let's do this thing. Continuing on through chapter 3 here. So we did exponential last time. We're going to jump to what ties with exponential here momentarily. But before we do that, to kick off, the exponential function f of x equals 13.49 times 0.967 raised to the x minus 1 describes the number of O-rings expected to fail when the temperature is x degrees Fahrenheit. Find the number of O-rings expected to fail when the temperature is 31 degrees Fahrenheit. So that's going to be our x. So we're going to put this in. F of 31 equals 13.49 parentheses 0.967 raised to the 31st minus 1. So if we take our calculator, and so we do 13.49 parentheses 0.967 close parentheses raised to the 31st. Make sure you arrow to the right to get out of the exponent. And then minus 1 equals 3.766, so 3.77. Now, we can't have, if part of an O-ring fails, it's a whole O-ring that fails. It can't be, well, 3.5 O-rings failed. No, 4 of them did. So we're going to round this up to 4 O-rings. And that would be our solution. So that was exponential. So there we had the exponent in the, or that was the variable, the base, and actual number. But we're going to shift now to logarithmic functions. And so here's definitely, or the definition of a logarithmic function. So it's going to be in the form of y equals log base b x, which is going to be equivalent to by equals x. So what this is doing is it's finding what exponent would be this base in order to get this number. So b the base, y the exponent, x would be your solution. Okay, so think the number x banded out to whatever that exponent will take you to. So our base function, a lot of times what you'll see is f of x equals log base b of x. So our base b, so if it's log 5, 5 is our base. So keep in mind, logarithmic form would be y equals log base bx. So that ties to exponential of by equals x. So we're going to convert back and forth between these two to begin with. So if we write the following as an equivalent exponential form. So right now they're in logarithmic form. We're going to write them as exponential. So we start with our base. Base is what's in front of the log. So here we're base 5 with the y being what's in front. So in front's a 2, so 5 squared would equal our x here, which is what's alongside the back here. So equals x. So equals x. Now, in a little bit here, we'll actually go through and we'll solve these out. But right now, we're just changing it to the other form. Now, looking at this, doesn't always become clear how to solve it. So sometimes we're going to convert it over to this and be able to solve it out that way. So, again, set it up. Start with your base. Base is what's in front of the log. So this would be base b raised to our exponent 3 equals our what's next to that, which is our 64. So after the b is the base, and then it's our expanded out number. So our expanded out number is 64. So b to the third is 64, and then we could solve for what is b. We're also going to go from logarithmic, or from exponential to logarithmic form. So if you look back up a little bit further there, so our base b is going to be the big number that we're raised to that power. We're going to be equal to that exponent, and then what we're equal to on this side with our exponential for logarithmic will be our big number that we're looking to find. Here, e is our base, so we're log e equals y with the 9. So what we're going to expand it out to be goes on the backside. E is in our base, so the big number that we're raised to an exponent to, and it's going to equal the exponent. Okay. So, to solve these, so evaluate each one here. So, when we do this, we're going to, before I said we'll sometimes have to switch it over, we're going to switch it over all the time. So, to start off with, you start with your base. So, the little number after the log is your base. We don't know an exponent. It's not equal to anything, so we put a variable there. Equals the big number here. So that's what we're going to want to expand this out to. So if you think about it, we need to get our same base first. So 2 to the x is going to be equal to 2 to some power, so that we get our 16. So 2 to the first is 2, 2 squared, 4 to the third is 8, 2 to the fourth gives us our 16. So once you have the same base, you set the exponents equal to each other. Now in this case, that's as far as we got to go. So x will equal 4 in this case. But if it was, say, a 2x, then you would keep going, keep solving to finish that one out. Okay. So similar thing here. So log base 25 equals 5. So my base, 25, and we don't have a variable, so x, equals our big number 5. Now in this case, 5 raised to a certain power isn't going to change it so much. But we can reduce the 25 to make this 5 squared, which is raised to the x. So this is technically 5 to the first. Now, if we have a power to a power, we can rewrite this as 5 times 2x, because power to a power, you multiply them, will equal 5 to the first. So in other words, 2x would equal 1. So the exponents, once we have the same base, we set the exponents equal to each other, and we would divide by 2 to get x by itself, and so x would equal 1/2. Okay. So, questions with this stuff as you go through, remember, you can always pause to write stuff down, you can rewind it to watch it again and catch something. Otherwise, email me, pan me, send me a message on Google Classroom, all different ways that you can get a hold of me and I can help you out. Now, some basic logarithmic properties that involve 1. Well, log base b, looking for b, is going to be 1. So it's going to be 1 because the exponent to which we must raise b to obtain a b is just b to the first. So remember, this is the number we're looking to get. This is going to be b. Log is saying b, your base, raised to what power gives you this number? Well, b to the first is b. Now, if you have b and you're looking for a 1, it's automatically 0 because anything to the 0 power is going to be 1. So b to the 0 would equal 1. Okay? So if you had something like this where it was log base 7 and we're trying to get to 7, well, its exponent's going to be 1 because 7 to the first is 7. So remember, this is always going to be the number that you want to end up in the end. This is your base. You're going to want to raise it to a certain power in order to get this end number. Inverse properties of logarithms. So if we have log base b of b raised to the x, well, this is saying, okay, so b raised to what exponent will give you this? Well, clearly this exponent is what we're looking for. So in that case, the b's cancel out and it's just going to be that x. If we're the other way, b raised to a certain log, again, it's saying b raised to a power. Well, this log is saying, hey, what power are we going to raise to? Well, it's whatever this is. Okay. Now, as far as logarithmic functions go, they're going to be the inverse graph of your exponential. So if we did 2 to the x, which we did the last lesson, we would be this blue line curving. Well, it being the inverse, so if we had the dashed line here of y equals x, inverse is going to flip over that line. So if it's curving up, this one here is coming up and curving out to be our logarithmic function. So exponential will start flat, curve up. Logarithmic will be coming up and curving and flatten out. So some of those characteristics. So they're going to kind of share and they tie to what we did for exponentials because they're tied together with their graph. So for this, the x-intercept is going to be 1, and there's going to be no y-intercept. The last one, we had a x-intercept that didn't exist, but our y-intercept always went through 1. So they're flipped around. They're this opposite thing of what we did with exponentials. The y-axis, or x equals 0, is going to be a vertical asymptote. With an exponential, it was the y-axis that we went through, so the x-axis was our horizontal asymptote. So in other words, y equals 0, horizontal asymptote. X goes to 0 from the right, then our logarithm is going to go to either negative infinity or infinity. So as we get closer to 0 from the right, if I go back up here, as we get closer, we're either going to curve down to negative infinity or we're going to curve up to positive infinity, but we're going to go to one or the other. As long as b is equal or greater than 1, if b is greater than 1, so if our base is a bigger number than 1, our function is going to be increasing as we go. If we're between 0 and 1, then it's going to be decreasing, so that's where this is going to flip over and be going the other way, our graph. Now, keep in mind this graph is a smooth curve and it's continuous. There are no sharp corners or gaps, so there's no places where we jump or have breaks in it. It's just one smooth curve that's curving as we go up from the y-axis, curving flat or to flatten out then with our graph. So we can do transformations just like with exponentials. So if we add or subtract on this back side, that's going to shift it up or down. If we add or subtract on the inside with that x, that the number we're trying to get to in the end, then it's going to shift it left or right. And remember, it's always opposite. So negative goes right, positive goes left. If we do on the outside, so on the outside of it, it's going to reflect across the y-axis. So it's going to flip it horizontally, or x-axis, sorry, x-axis, so it'll flip it vertically. On the inside, it'll do it horizontally, which makes sense because the outside's vertical, inside's horizontal. So here it reflects across the y-axis. So on the inside, left and right, outside, up or down. Timesing on the outside is going to make it taller or skinnier. Obviously, the bigger the number, the taller it'll be. It goes the same way. If it's on the inside, it'll make it wider or shorter. And the bigger the number, the skinnier it will be. So, for example, 3 plus, and a lot of times you're actually going to see it in front here, so we don't get it confused with, okay, is it part of x, is it not, or are we taking it plus the log the whole thing? But 3 plus the log 4x is the graph of g of x equals log base 4x just shifted up 3. So because it's plus 3 on the outside, we're going to take it and we're just going to move it up. If that's log base 4 of x would be our original. As far as domain goes, so you might have noticed, we're never going to cross that y-axis. So in this case, your domain is going to be all reals that are positive, so everything greater than 0. But its range could be anything, all reals. So like the domain here. Now, because we've been shifted, that's going to shift our domain because we're shifted left 3. So instead of being greater than 0, our domain is going to be x is greater than negative 3 because we're shifted left 3. So that's going to shift the domain left 3. Okay? So if you think about it, if you put negative 3 in here, negative 3 plus 3 is log of 0, we're still going to be good because we're going to get an exponent of 1. So we're still positive. You know, if we did, say, negative 2, well, negative 2 plus 3 is 1. So this would be log base 0 to get 1. So those would work. So we're still good. Once we would go below this, say negative 4, well, now we're negative 4 plus 3, which is log of negative 1. There's no way to get a negative 1 based off of the exponent in that sense. So, common logs. The common log is log base 10. So that's where you'll see it just as log. there is no base. So when there's no base, that means it's really log base 10 to do it. So like if we did here, find the value of log this, so then there's no thing there, so that'd be base 10 of 10,000. It's saying 10 to what power is going to give us 1,000. 1,000, not 10,000. I misspoke. Sorry. Well, we'd move it once, twice, 3 times to be 10 to the third, which would be 1,000. So 3 is going to be that value. So what this is saying is log of base 10 is 1,000. So 10 to what power is 1,000? Well, 10 to the third. Right? So the percentage of adult height attained by a boy who is X years old can be modeled by f of x equals 29 plus 48.8 log of x plus 1, where x is the boy's age and f of x represents the percentage of his adult height. Approximate what percentage of adult height has the boy attained at age 8. So 8 is going to be our x. So we're going to find f of 8. So 29 plus 48.8 log of 8 plus 1. So in other words, 29 plus 48.8 log of 9. Now again, notice how we don't have a base, so we're dealing with log of base 10. Now if you go into your calculator here, we have log right here by the 7. Notice how it's just regular log, and if I hit log, it will show up as log with no base to it. The log in your calculator is log base 10. So if it's any other base, we're going to have to either change the base, which we'll talk about later, or it's going to be something that we could figure out without using a calculator. But if it doesn't have a base to it, that's log base 10, and that's what's on a graphing calculator that you could use, or even just a regular calculator for that matter. So has to be log base 10 to do the calculator. So if we do this one here, let me clear this out. So we are 29 plus 48.8 log of 9, close your parentheses. So that's what it looks like. So 29 plus 48.8 log of 9. So when I hit enter, I get 75.57. And that would be a percent. Now, typically, when we're dealing with percents, we don't really like decimals. So what we'll do is we'll round to the nearest whole percent. So we're going to say is this going to be is about 76% then. Okay. So, again, have questions with this. Remember, you can always rewind and watch something again, or you can pause it to write stuff down. Otherwise, again, always you can email me, pan me, send me a message on Google Classroom. Now, some properties of logarithms. So, just like with what we kind of talked about before, but our base, in order to get 1 with that base, the exponent has to be 0. Well, that's the same thing with common logs. So if it's log base 10 and all we have is a 1 here, obviously it has to be a 0 because anything raised to the 0 power is our 1. Before we talked about if we had log base b and we're looking for b in the end, it's just going to be 1 because again, b to what power is b? Well, b to the first. Same thing here, but it has to be in tens. So log of 10 would be 1 since we're log base 10. Log base b of b raised to the x. So if we're looking for a number here and it is a base raised to a number, if it's the same base as what we got here, it's just going to be what that exponent is. Same thing here. We're log base 10, so if it's 10 raised to a certain power, the log and the 10 really, if for all practical purposes, cancel out and you're just left with that exponent of x. Same thing here. If we have our base and we raise it to that log of base b, so the same base in the log, it's just going to be whatever that number is on the back side. Same thing with log base 10. If it's 10 raised to that log base 10 of x, it's just going to be x. So when we have log of 1,000, again, log base 10. So 10 to what power gives me 1,000? Well, 10 to the third. So x would equal 3 there. If I made that an x. All right, so let's work some problems. So the magnitude R on the Richter scale of an earthquake of intensity I is given by R equals log of I over I naught. So the I sub 0 is I naught. Where I naught is the intensity of a barely felt zero level earthquake. So the earthquake that destroyed San Francisco in 1906 was 10 raised to the 8.3 times as intense as a zero level earthquake. What was its magnitude on the Richter scale? So if we set this up, R equals log. Now our intensity, it said, was 10 to the 8.3 times as intense as a barely felt zero level earthquake. So zero level earthquake was I naught, so it'd be 10.83 times I naught, and it's over our I naught, our original intensity, which is a zero level earthquake. So because it was 10.83 times as intense as a zero level, that's why I did 10.83 I naught. Now, nice thing about that, I naughts cancel, so we no longer have to worry about it. All we have is just log 10, 8.3. Well, again, log is, there's nothing here. This is always base 10. So what this is saying is 10 to what power gives me 10 to the 8.3? Well, 8.3. So whenever it's the same base as what you have here, you just got to write the exponent, and that's all you have to do. Okay. Next, we have the natural logarithms. The logarithmic function with base e is called the natural logarithmic function. So in other words, the natural log is usually how we refer to. So this is really what ln stands for, is the log of base e of that number. So we would just shorten it to lnx, which is standing for the logarithm of a base e number, the natural number. Or natural base, I should say, not natural number, but natural base e. So, for whatever reason, they did natural log as ln instead of nl. I don't know if they just didn't want to be confused with the National League of Baseball or what there, but for whatever reason they went ln. So ln is our natural log. So if we wanted to find the domain of this function, well, right here it says the domain of the natural logarithmic function, so the natural log is the set of all positive real numbers. But what's going to happen here? Well, we know that the ln has to be greater than 0. So what we're going to do is we're going to take whatever's inside here, and we're going to set that to be greater than 0. And then we can solve for x, and that will allow us to find what this domain is actually going to be. So if we add the x over, we'd hit 3 is greater than x, so I added x. So 3 is greater than x, in other words, x has to be less than 3 in this case. Which makes sense because we have a negative x, so that should flip it over. So instead of being all the positives, we're going to be the negatives. And then because it's plus 3, we're actually shifted to the left 3. So we're going to be opposite way here because of the negative on the x, yeah. So it should go to the right x, or 3 times, sorry. Well, okay, so it would be left 3 and then we flip it with the negative. That's where I'm going with this. Wow, I'm sorry. I apologize. But that's what's going on here. So we solved it out, and that's what's giving us what our domain is. Okay. But otherwise, it does the transformations just like the other stuff. So last few things here. First off, properties of natural logs, just like with general logs. Natural logs are going to have those same things. So when we said it's log base b, and we want 1, in order to get 1 for our final answer, it has to be log, the exponent has to be 0. Same thing here. ln of 1 is 0. If we have the base and we're trying to get that base, it's going to be 1. So if we did the natural log of e, so that what that's saying is log base e to get e has to be 1. If we take log base b raised, and then we're looking for b to the x, we got x. Well, same thing here. Natural log of e raised to the x is going to be just that variable. And if we go the other way, e to the ln of x, the e and the ln, think of it as a way of that cancels out, and you're just left with whatever that number is, that x. So for example, if we did e to the ln of 2, really that part's canceling out, and we just have 2 left over, which is why it's 2. Now, when the outside air temperature, wow, if I could talk. When the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. So while that may not sound all that hot on the outside, inside it's going to rise really quick. This is why they say you don't leave your children in the car, because this is what's going to happen. It's going to raise it really fast, and it's going to be a cooker in there, and it's going to hurt your children. So please, children, pets, anything, you don't leave them in a locked car in the summer. Not so good, even in the wintertime. You just don't leave your kid in the locked car, because it can really do bad things. The function f of x equals 13.4 ln x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 15 minutes. So if x is our number of minutes, we're going to set this up of f of 50. So in other words, 13.4 ln of 50. Now, I was always taught you do the L kind of a cursive way so that it doesn't look like one N. So that's why I'm doing the ln of 50 here. Minus 11.6, so we can put this in our calculator. So 13.4. Now, the ln button is here right next to the 4, just below the log. So we had ln of 50 minus 11.6. So we get 40.82. Now it's set to the nearest degree. So this would equal approximately 41 degrees. And that's it. That's this lesson. So please, if you have questions, again, email me, pan me, send me a message on Google Classroom, and I will try to help you out as best I can. Otherwise, you can always, again, pause the video and write stuff down if you need to, or rewind it and hear it again. Say you want to go through the first time and write stuff down, then back it up, and then listen as you go through it. Whatever you need to do, make it work. Otherwise, until next time, we'll talk to you later.